we have seen about the formation of cubic close-packed structure in 3 dimensions. How was it formed? Can you tell me how it was formed?
by joining square closing layers.
Square close-packed two-dimensional layers when they are stacked one over another in such a way that both horizontal as well as vertical alignment is present, then that will lead to cubic close-packing. And we have seen then cubic close-packing in 2 dimensions is not completely utilizing the entire space available. So it is not effective, and we have seen that hexagonal close packing is more effective compared to cubic close packing. And let us see the packing in 3 dimensions for hexagonal close packing. Hexagonal close packing. Okay. Now, so this is the hexagonal close packing. So when hexagonal close packing is done in 2 dimensions, it is effectively. Can you see this board?
Yes, sir.
Yes,
Yeah.
sir.
It is. You cannot see.
We can see, sir.
We can see, sir.
Oh, okay. Okay, okay. It is effectively occupying more space, and we say that is more efficient. And in this case, you'll have two types of trigonal or triangular voids. These empty spaces are known as voids. Empty spaces will be known by the name voids. Okay. So it will be known by the name void. So you'll find two types of voids, where in one type of void, you'll have the triangular uh, a triangle facing upwards, and the second case where the triangle words the apex facing downwards. Two types of words will be there. Here, in here you can see that it is facing upwards, and in this layer it is facing downward. Here which is facing upwards, and here it is facing downwards. Okay, so triangular words are formed in hexagonal cross packing. Now let's see. We are going to place another layer over this layer so that it is placed in the depressions. So let us say that the second layer is placed over these voids, the voids which is in which the triangular faces or apex is pointing downwards. We are going to place over this layer. Okay, we are going to place over this layer. Now here in the second picture, in this picture, it is shown like that. The dotted lines represents like that. Is it possible for the second layer to occupy both these voids which is having apex upwards as well as downwards? Is it possible? Is it possible for
No,
you
sir.
to arrange? Is it possible for you to arrange the second layer over the first layer in such a way that it will occupy or it will cover both these types of triangular voids? Is it possible?
No,
No,
sir.
sir.
No. Either it can be placed on this type of words, or it can be placed this type of words. So in this example, in this figure which I have shown, the second layer is placed over the words which is having apex at the pointing downwards. So this is the arrangement. Okay, this is the arrangement. Now, can you say that if I call the first layer as A, can you call the second layer as A? Is it similar to first layer in all respect in their alignment?
No, sir.
No.
No, sir.
So if I call the first layer as A, the second layer should be called as B. Second layer should be B. Okay. Second layer should be called as B. Now you can see that now I'm going to place a third layer over the second layer. So the second I have placed the second layer over these words. Okay, these words. Now that will generate when I am placing a third layer, which you can see here. The third layer can be placed over the second layer in such a way that it will occupy the tetrahedral words or it will occupy the octahedral words. So in this case, here in this figure, you take this figure, you take this figure. Okay. Now you consider this void which is marked as B, which is marked as B. How many atoms are present uh, in this void, in this empty space? Close to this empty space, how many atoms are present?
3. 3.
1, 2, 3, and one in the downward layer, the backside layer. So these dotted lines represent the backside layer. So four spheres are forming this void. Four spheres are forming this void. Okay. Now, if you join the centers of these four spheres that will form this void, you will get a tetrahedral shape. You will get a tetrahedral shape. That is why we call it as a tetrahedral void. So this will be forming a this point will be forming a tetrahedral void. Now, if you look at the other one here, if you take this upper layer, is it completely covering this the word C? Is the second layer completely covering the word C? Here you can see that the second layer, this is what I told as tetrahedral words. There's one at the back, 3 in the front that will form the tetrahedral words. The other type of word will also be formed where the entire void will not be covered fully. So you can see that first layer, second layer, as well as the third layer is not able to cover these voids completely. So when you join the spheres that is forming this void, you will get an octahedral shape like this. Here you can see that this is the tetrahedral void, this is tetrahedral void, and here it will be forming the octahedral void. And at the same time, you will not be able to cover both the tetrahedral as well as octahedral voids. Okay. Now, if I am placing the fourth layer, if I am placing the third layer, it can be placed over the tetrahedral void or it can be placed over the octahedral void. If I am placing the third layer over the tetrahedral void, then I can say that the layer, first layer will be similar to third layer. This is the first layer. Let me consider this as the first layer. This is second layer. If I place the third layer over the tetrahedral void, it will be aligning with the first layer. Okay. And if I place the third layer over the octahedral void, first layer will be different from the second layer and the third layer will be different from the second layer. Okay, so all the three layers will be different. And by placing the fourth layer alone, you will have similarity between first and fourth layer. So if I place the third layer over the tetrahedral void, then first layer will be similar to third layer. If I place the third layer over octahedral void, then all the three layers will be different. Only by placing the fourth layer, there will be the correlation between first layer as well as the fourth layer. So if I place over the tetrahedral voids, if I call the first layer as A, what will you call the second layer? Is it similar to A? It is not similar, so it will be B. And if I am placing the third layer over tetrahedral void, then I can say that the third layer will be similar to the first layer. So third layer will be A, fourth layer will be B, fifth layer will be A. So such a type of packing where it covers the tetrahedral void, that will be called as uh, AB type packing in 3 dimensions. AB type packing in 3 dimensions, and the structure so produced will be called as hexagonal close pack structure in 3 dimensions. hexagonal close pack structure in 3 dimensions, where it is the what is hexagonal close pack structure? It is AB type. That means first layer will be different from the second layer, but there will be alignment between first and third layer. Every alternate layers will be aligning themselves. So such structure will be called as HCP, which stands for hexagonal close pack structure. Stands for hexagonal hexagonal close packed structure. We'll call it as HCP. HCP in 3 dimensions. Okay, and this type of structure will be seen with the magnesium zinc. Such metals will show this HCP structure. So, can you tell me what is the peculiarity of the hexagonal close pack structure? What is the peculiarity of the hexagonal close pack structure? Can you hear me?
Yes, sir. Yes, sir.
Yes, sir.
Sir.
Yes.
Yes, sir.
What is the peculiarity of hexagonal close pack structure?
So gap is minimized.
Is it? Yeah, I told you
More efficient.
when you are arranging the second layer, there will be we call hexagonal close pack structure will be called as AB type in 3 dimensions. There will be perfect alignment between first and the third layer. First and the third layer. So that type of arrangement in 3 dimensions, that will lead to hexagonal close pack structure in 3 dimensions, where we are placing the third layer over the tetrahedral words. Tetrahedral words. Okay, and when we are placing the third layer over the octahedral voids, then first layer will be different from second layer will be different from third layer, and when you are placing the fourth layer, that fourth layer will be similar to first layer. So that type of arrangement will be called as ABC type arrangement, or ABC type of packing. And ABC type packing will lead to face-centered cubic structure. What is the peculiarity of face-centered cubic packing? It is ABC type, where every fourth layer will align with the first layer. Every fourth layer will align with the first layer, and you can see that the fifth layer will align with the second layer. Sixth layer will align with the third layer. So likewise, it will go on, and therefore we call it as face-centered cubic FCC. We call it as FCC. That will lead to FCC structure, face-centered cubic. Face-centered cubic structure, or it can also be lead to cubic close pack structure, CCP. CCP is also known as FCC, cubic close pack in 3 dimensions. CCB in 3D, not 2 dimensions. So FCC is also known as CCP. Okay, or cubic close pack structure is known as FCC, face-centered cubic structure. And you can see that copper, silver, all will lead to cubic close packing or FCC structure. So in 3 dimensions, when you arrange over hexagonal close pack structure in 2 dimensions, that will either lead to HCP, hexagonal close packing, or cubic close packing, cubic CCP, cubic close packing, which is also known as FCC. And you can see that both HCP as well as CCP are equally efficient. Both are equally efficient. So what is the structural difference between them? In hexagonal close packing structure, every third layer will align with the first layer. Okay, and in FCC or cubic close packing structure, every fourth layer will align with the first layer. That is the difference between these two. Are you getting? Are you getting?
Yes, sir.
Yeah, and as I told you, both are effective, and they both will occupy maximum amount of space. But the simple cubic structure that we have seen, where a type of parking is taking place, which is not effective and not efficient, it will not be utilized in the entire space available for them. Okay, now who is there? Yeah, Srigant. Srigant. Yeah. So you take a what is it? Screenshot of these the people who are available and send me in WhatsApp. Okay, members who are available in the class, you just take a screenshot and tell me, send me. Okay, these 27, 27, only 25 have joined. So let me see about others also. So just send it. Okay. So that is about cubic close packing and hexagonal close packing. And two types of voids we have seen. Empty spaces are formed. What are the two types of empty spaces formed? And the number of tetrahedral words and the octahedral words depends upon the number of the constituent particles present. It depends upon the number of constituent particles present. If you have n number of particles, atoms or molecules or ions, if n is the number of constituent particles, then you will have n number of same number of same number of octahedral words, and 2n number of tetrahedral words. So if I ask you, in a face-centered cubic structure, what is the number of unit cell I am talking about, I am face-centered cubic unit cell, what will be the number of tetrahedral words as well as the octahedral words?
4 octahedral voids and 8 tetrahedral voids.
Yeah, the number of atoms is 4, so therefore there will be 4 octahedral words, which is equal to the number of atoms present, and there will be double number, that means 8 tetrahedral words. What about body-centered cubic structure? Body-centered cubic?
2 and 4.
2 and 4. 2 octahedral void and 4 tetrahedral words will be present. 2 and 4 will be there. So you can see that triangular words in the second layer are above the triangular words of the first layer, that we are talking about the arrangement of the second layer, and the triangular shapes of this do not overlap. One of them will have apex of the triangle pointing upwards, and the other one words have marked, which is having marked as O. Such words are surrounded by 6 spheres and will lead to octahedral words. And as I told you, if n is the number of atoms, then octahedral words will be n, and 2n will be the number of tetrahedral words. And this is the structure of a tetrahedral void as well as the octahedral words formed. 6 spheres will be surrounding the octahedral void, and 4 spheres will be surrounding the tetrahedral void. 4 spheres will be surrounding the tetrahedral void. And covering the tetrahedral words, these all things we have discussed. AB type pattern will lead to HCP, hexagonal close pack structure, which is seen with the magnesium and zinc. This is hexagonal close pack structure, AB type packing. Then uh, ABC type structure, that will be called a CCP or face centered cubic structure, and copper and silver crystal will have such a structure. This is the tetrahedral word and octahedral word, and you can see the ABC type packing, ABC layer. So every fourth layer will have alignment similar to the first layer. So that is about and as I told you, both are equally efficient for covering the empty spaces. Okay. Now, before going to the packing efficiency, we'll see how to find the formula of the compound from the number of tetrahedral words as well as the number of octahedral words. Okay. And as I told you, the number of tetrahedral words as well as the number of octahedral words depends upon what? Number of tetrahedral and number of octahedral words depends upon what?
Number of
Number of
atoms.
constituent
Number of atoms present. Okay.
Number of particles.
Number of atoms. Normally, all the tetrahedral words as well as all the octahedral words will not be occupied. Will not be occupied. Okay. And normally, what happens is that in ionic crystal, the bigger ions, that means the anions, that will form the crystal lattice. That will form the crystal that will be occupying the body center, face center, as well as the corners. And you can see that the smaller cations that will occupy the voids. That will occupy the words. And if the cations are very small, it will occupy the tetrahedral words, and if it is slightly larger, it will occupy the octahedral words. And we cannot say that all the tetrahedral as well as all the octahedral words are covered by the cations. It will not be will not be so. Okay, so we'll see how to find the formula of a compound based on the number of tetrahedral words and as well as octahedral words covered. Just note down this question. A compound is formed by two elements. A compound is formed by two elements. X and Y. Y atoms make CCP, cubic close packed structure. Uh, so what will be X, Y? Will it be cation or anion?
anion.
It will be anion. Anion, bigger sized ions will occupy the will form the crystal lattice, and X atoms, which are the cations, occupy all the octahedral words. They occupy all octahedral words. All octahedral words. What is the formula of the compound? So Y atoms forms the CCP. Y atoms forms the CCP. X is the cation. So Y forms CCP means if one Y atom is present in a unit cell, what will be the number of octahedral words present? If one Y atom is present, what is the octahedral words? Here the not tetrahedral
One.
words is okay, but it will be one, same as the number of atoms. If two Y atoms are present, what will be the number of octahedral words?
Two.
Two. If three are present, then there will be three octahedral words, and it is given that all what is the formula of the compound? So X, what about A atoms? A are cations that are occupying the voids. So the number of atoms present in the cubic lattice, that will be given by the B atoms. Okay. So we are having B as well as A as well as B. Let us say that there are XB atoms. Then we how many tetrahedral words will be there?
2x,
2x.
Tetrahedral words will be 2x will be the tetrahedral words. And out of 2x, what is the fraction occupied?
2 by third,
2
Okay.
by 3.
2 by
So
third.
A will be occupying this much 2x tetrahedral words will be there, and out of that 2 by third will be 2 by third of 2x will be occupied by A atoms. Am I right? Am I right or not?
Yes, sir.
Yes, sir.
Yeah. So if you are taking the ratio between A and B, it will be 4x by 3, and here it will be x. If you take ratio, what will be the ratio? 4 by 3 is to 1 will be the ratio between 4 by 3 is to 1 will be the ratio between A and B. Or if I multiply throughout by 3, what will be the ratio? It will be in the ratio 4 is to 3. So what should be the formula of the compound then?
A4B3,
It should be in the ratio A4B3. A4B3. Are you getting? I will pause for a moment. If you have any doubts, you can ask me now. If you want, I will explain again. So it is made of A and B. B forms the lattice. So let the B atoms be X. Therefore, tetrahedral words will be equal to 2x. Tetrahedral words occupied by 2 by 3 of 2x, that is equal to 4 by 3x. Ratio of A and B, it will be uh, it will be 4 by 3 x is to x, or 4 by 3 is to 1, or you can write 4 is to 3. That means A will be 4, B is equal to 3. So formula of the compound will be A4B3. Any doubt? So this is our figure. A cubic closed structure where only one face is shown. At the center of the face, we are having an atom. Now, let me say length of the edge, length of each edge. It's a cube. Let it be A. So I can say that C. What is AC? It is the face diagonal. Face diagonal. Let the face length of the face diagonal be B. And if you take the triangle, right angle triangle, ACD, ACD, we can say AD square plus DC square is equal to AC square. Am I right? Or not?
Yes, sir.
Yes,
What is AD? What is the value of AD? AD is edge length. What is
A.
root 2 A? B is equal to root A. Am I right?
Yes, sir.
Yes, sir.
Sir.
Yeah. Now let me say, let R, small letter R is the radius of the atom, radius of the sphere. And what will be B in terms of R?
4R.
How many R's are there?
4R.
4R.
One, this one diameter is present here, radius, here also radius. So it will be equal to 4R. So we can say root 2A, B is nothing but root 2A is equal to 4R. Root 2A is equal to 4R. This relationship you have to keep in mind. Okay. Now we are going to find the parking efficiency. We are going for the parking efficiency. Parking efficiency is equal to volume occupied by all spheres by the total volume into 100. Total volume into 100 will give you parking efficiency. Out of the total volume, how much is
4.
in FC? Here we are talking about face centered. In face centered cubic structure, how many spheres will be there? And what is the volume of a sphere of radius R?
4 by 3 pi r cube. 4 by 3 pi r cube.
It will be 4 by 3 pi r cube. Okay, it is equal to 4 by 3 pi r cube. Now, total volume occupied by all the spheres. So, what is the volume occupied by all the spheres? That we can write. 4 spheres are there, and each is having a volume of 4 by 3. It is equal to a cube. So, total volume is a cube. So, out of the total volume, 4 atoms are occupying a volume equal to 4 into 4 by 3 pi r cube divided by a cube into 100 will give you the parking efficiency. Now you can relate between R and A. What is the relationship between R and A?
Root 2A is equal to 4R.
Root 2, we have the relationship root 2A is equal to 4R. Or what is R? A by 2 root 2.
Yes, sir.
R is equal to A by 2 root 2. Okay. And what will be A? 4R by root 2. What is 4R by root 2?
2 root 2R.
R. So this relationship between A and R in terms of the other one. Okay. Now let me say, if let me substitute this A in terms of R. A is substituted in terms of R. So 4 into 4 by 3, pi value 22 by 7, R cube divided by A cube is 2 root 2 R all cube. Okay, so it will give you 16 by 3 into 22 by, it just simplify into 100 is there, 22 by 7 into R cube divided by 2 cube, 8. What is the value of root 2? 1.414 all cube R cube. R cube and R cube get cancelled. You simplify these terms. When you simplify, you'll get an answer which is equal to 74%. Calculation you can do it later. So you are having a packing efficiency for HCP as 74%. Okay. So this you have to learn how to find the packing efficiency for a body centered cubic. Here we have seen about a face centered cubic structure. Did you get? Did you understand this concept?
Yes, sir.
Yes, sir.
Yeah. So this is the relationship. This thing or is already uploaded. If you can take it from there itself, okay, and you will get the packing efficiency as 74%. That is for a HCP or face centered cubic structure. Okay. Any doubts?
No, sir.
No. So it's almost 45 minutes. We will stop. Okay. So the other two packing efficiency we'll discuss tomorrow morning, and tomorrow afternoon also we'll have these classes at the same time. So by 2-3 classes we'll try to complete this chapter, and we'll go for the next organic chapters. Okay. So I hope the topics that I covered. So today after this one we completed the packing, cubic close packing in 3 dimensions, which forms HCP as well as FCC. Both are efficient. Both are having an efficiency of 70. Both HCP as well as CCP will have an efficiency of 74%. That is the thing that you have to keep in mind. The rest of the things we'll see tomorrow. Thank you.
Thank you, sir.
Thank you, sir.
Great.